In this and the next few videos, I want to tell you about a machine learning application example or a machine learning application case study centered around an application called Photo OCR. There are three reasons why I want to do this. First, I wanted to show you an example of how a complex machine learning system can be pulled together. Second, I want to talk about the concept of a machine learning pipeline and how to allocate resources when you're trying to decide what to do next. And this can be either in the context of you working by yourself on a big application, or it can be in the context of a team of developers trying to build a complex application together. And third and finally, the Photo OCR problem also gives me an excuse to tell you about just a couple more interesting ideas for machine learning. One is some ideas on how to apply machine learning to computer vision problems, and second is the idea of artificial data synthesis, which we'll see in a couple of videos. So let's start by talking about what is the Photo OCR problem. Photo OCR stands for Photo Optical Character Recognition. With the growth of digital photography and more recently the growth of cameras in our cell phones, we now have tons of digital pictures that we take all over the place. And one of the things that has interested many developers is how to get our computers to understand the content of these pictures a little bit better. The Photo OCR problem focuses on how to get computers to read the text that appears in images that we take. Given an image like this, it might be nice if the computer can read the text in this image so that if you're trying to look for this picture again, you could type in the words, Lulubee's Antique Mall, and have it automatically pull up this picture so that you're not spending lots of time digging through your photo collection of maybe hundreds or thousands of pictures in order to find this. So the Photo OCR problem does exactly this, and it does so in several steps. First, given a picture, it has to look through the image and detect where is there text in the picture. And after it has done that, or if it successfully does that, it then has to look at these text regions and actually read the text in those regions. And hopefully, if it reads it correctly, it'll come up with these transcriptions of what is the text that appears in the image. Whereas OCR, or Optical Character Recognition of scanned documents, is a relatively easier problem, doing OCR from photographs today is still considered a very difficult machine learning problem. And if you can do this, not only can this help our computers to understand the content of our outdoor images better, there are also applications like helping blind people. For example, if you could provide to a blind person a camera that can look at what's in front of them and just tell them what are the words that may be on the street sign in front of them. And there are also researchers today working on Photo OCR to help with car navigation systems. For example, imagine if your car could read the street signs and help you navigate to your destination. In order to perform Photo OCR, here's what we can do. First, we can go through the image and find the regions where there's text in the image. So shown here is one example of text in the image that a Photo OCR system may find. Second, given the rectangle around that text region, we can then do character segmentation, where we might take this text box that says Antique Mall and try to segment it out into the locations of the individual characters. And finally, having segmented out into individual characters, we can then run a classifier which looks at the images of the individual characters and tries to figure out that the first character is an A, the second character is an N, the third character is a T, and so on. So that by doing all that, hopefully you can then figure out that this phrase is Lulubee's Antique Mall, and similarly for some of the other words that appear in that image. I should say that there's some Photo OCR systems that do even more complex things, like a bit of spelling correction at the end. So if, for example, your character segmentation and character classification system tells you that it sees the word C1EANING, then a sort of spelling correction system might tell you that this is probably the word cleaning, and your character classification algorithm had just mistaken the L for a 1. But for the purpose of what I want to do in this video, let's ignore this last step and just focus on a system that does these three steps of text detection, character segmentation, and character classification. A system like this is what we call a machine learning pipeline. In particular, here's a picture showing the Photo OCR pipeline. We have an image which is then fed to the text detection system, And having detected the text regions, we then segment out the characters, the individual characters in the text, and finally we recognize the individual characters. In many complex machine learning systems, these sorts of pipelines are common, where you can have multiple modules, in this example the text detection, character segmentation, character recognition modules, each of which may be a machine learning component, or sometimes it may not be a machine learning component, but to have a set of modules that act one after another on some piece of data in order to produce the output you want, which in the photo OCR example is the final transcription of the text that appeared in the image. If you're designing a machine learning system, one of the most important decisions will often be exactly what is the pipeline that you want to put together. In other words, given the photo OCR problem, how do you break this problem down into a sequence of different modules? And your design of the pipeline and the performance of each of the modules in your pipeline will often have a big impact on the final performance of your overall algorithm. If you have a team of engineers working on a problem like this, it is also very common to have different individuals work on different modules. So I could easily imagine text detection easily being the task of anywhere from 1 to 5 engineers, character segmentation maybe another 1 to 5 engineers, and character recognition being another 1 to 5 engineers. And so having a pipeline like this often offers a natural way to divide up the workload amongst different members of an engineering team as well. Although, of course, all of this work could also be done by just one person if that's how you want to do it. In complex machine learning systems, the idea of a pipeline or of a machine learning pipeline is pretty pervasive. And what you just saw is a specific example of how a photo OCR pipeline might work. In the next few videos, I'll tell you a little bit more about this pipeline, and we'll continue to use this as an example to illustrate, I think, a few more key concepts of machine learning. In the previous video, we talked about the photo OCR pipeline and how that works, in which we would take an image and pass the image through a sequence of machine learning components in order to try to read the text that appears in an image. In this video, I'd like to tell you a bit more about how the individual components of the photo OCR pipeline works. In particular, most of this video will center around a discussion of what's called a sliding windows classifier. The first stage of the photo OCR pipeline was text detection, where we would look at an image like this and try to find the regions of text that appear in this image. Text detection is an unusual problem in computer vision because depending on the length of the text you're trying to find, these rectangles that you're trying to find can have different aspect ratios. So in order to talk about detecting things in images, let's start with a simpler example of pedestrian detection, and we'll then later go back to apply the ideas that were developed in pedestrian detection and apply them to text detection. So in pedestrian detection, you want to take an image that looks like this and find the individual pedestrians that appear in the image. So there's one pedestrian that we found, there's a second one, a third one, a fourth one, a fifth one, and a sixth one. And this problem is maybe slightly simpler than text detection just for the reason that the aspect ratio of most pedestrians are pretty similar, and so we can just use a fixed aspect ratio for these rectangles that we're trying to find. So by aspect ratio, I mean the ratio between the height and the width of these rectangles. So they're all the same for different pedestrians, but for text detection, the height to width ratio is different for different lines of text. Although for pedestrian detection, the pedestrians can be different distances away from the camera, and so the height of these rectangles can be different depending on how far away they are, but the aspect ratio is the same. In order to build a pedestrian detection system, here's how you can go about it. Let's say that we decide to standardize on this sort of aspect ratio, 82 by 36. And we could have chosen some rounded number like 80 by 40 or something, but 82 by 36 seems to work. What we would do is then go out and collect a large training set of positive and negative examples. So here are examples of 82 by 36 image patches that do contain pedestrians, and here are examples of images that do not. On this slide, I've shown 12 positive examples with y equals 1 and 12 negative examples with y equals 0. In a more typical pedestrian detection application, we may have anywhere from 1,000 training examples up to maybe 10,000 training examples, or even more if you can get even larger training sets. And what you can do is then train a neural network or some other learning algorithm to take as input an image patch of dimension 82 by 36 and to classify Y and to classify that image patch as either containing a pedestrian or not. So this gives you a way of applying supervised learning in order to take an image patch and determine whether or not a pedestrian appears in that image patch. Now, let's say we get a new image, a test set image like this, and we want to try to find the pedestrians that appear in this image. What we would do is start by taking a rectangular patch of this image, like that shown up here. So that's maybe an 82 by 36 patch of this image. And we'll run that image patch through our classifier to determine whether or not there is a pedestrian in that image patch. And hopefully our classifier will return y equals 0 for that patch, since there's no pedestrian. Next, we then take that green rectangle and we slide it over a bit, and then run that new image patch through our classifier to decide if there's a pedestrian there. And having done that, we then slide the window further to the right and run that patch through the classifier again. The amount by which you shift the rectangle over each time is a parameter that's sometimes called the step size of the parameter, sometimes also called the stride parameter. And if you step this over 1 pixel at a time, so if you use a step size or a stride of 1, that usually performs best, but is more computationally expensive. And so using a step size of maybe 4 pixels at a time or 8 pixels at a time or some large number of pixels might be more common, since you're then moving the rectangle a little bit more each time. But so using this process, you continue stepping the rectangle over to the right a bit at a time and running each of these patches through the classifier until eventually, as you slide this window over the different locations in the image, first starting with the first row and then with further rows in the image, you would then run all of these different image patches at some step size or at some stride through your classifier. Now, that was a pretty small rectangle that would only detect pedestrians of one specific size. What we do next is then start to look at larger image patches. So now let's take larger image patches like those shown here and run those through the classifier as well. And by the way, when I say take a larger image patch, what I really mean is when you take an image patch like this, what you're really doing is taking that image patch and resizing it down to 82 by 36, say. So take this larger patch and resize it to be a smaller image, and then there's this smaller resized image that is what you would pass through your classifier to try to decide if there's a pedestrian in that patch. And finally, you could do this at even larger scales and run that sliding windows to the end. And after this whole process, hopefully your algorithm will detect what are the pedestrians that appear in this image. So that's how you train a supervised learning classifier and then use a sliding windows classifier or use a sliding windows detector in order to find pedestrians in an image. Let's now return to the text detection example and talk about that stage in our photo OCR pipeline, where our goal is to find the text regions in the image. Similar to pedestrian detection, we can come up with a labeled training set with positive examples and negative examples, with positive examples corresponding to regions where text appears. So instead of trying to detect pedestrians, we're now trying to detect text. And so the positive examples are going to be patches of images where there is text, and negative examples are going to be patches of images where there isn't text. Having trained this classifier, we can now apply it to a new image, maybe to a test set image. So here's the image that we've been using as an example. Now, let's say we run, for this example, I'm going to run a sliding windows classifier at just one fixed scale, just for purpose of illustration, meaning that I'm going to use just one rectangle size. But let's say I run my little sliding windows classifier on lots of little image patches like this, right, over. If I do that, what I end up with is a result like this, where the white regions show where my text detection system thinks it has found text. And so the axes of these two figures are the same. So there's a region up here corresponds to a region up here. And so the fact that this is black up here represents that the classifier does not think it's found any text up there. Whereas the fact that there's a lot of white stuff here, that reflects that the classifier thinks it's found a bunch of text over there on the image. What I've done on this image on the lower left is actually use white to show where the classifier thinks it has found text, and the different shades of gray correspond to the probability that was output by the classifier. So lighter shades of gray corresponds to where it thinks it might have found text, but where it's lower confidence the bright white corresponds to where the classifier output a very high probability, estimated probability of there being text in that location. Now, for text detection, we aren't quite done yet, because what we actually want to do is draw rectangles around all the regions where there's text in the image. So we're going to take one more step, which is we're going to take the output of the classifier and apply to it what's called an expansion operator. So what that does is it takes this image here, and it takes each of the white blobs, takes each of the white regions, and it expands that white region. Mathematically, the way you implement that is, if you look at the image on the right, what we're doing to create the image on the right is, for every pixel, we're going to ask, is it within some distance of a white pixel in the left image? And so if a specific pixel is within, say, 5 pixels or 10 pixels of a white pixel in the leftmost image, then we'll also color that pixel white in the rightmost image. And so the effect of this is it'll take each of the white blobs in the leftmost image and it'll expand them a bit, so grow them a little bit by seeing what are the nearby pixels to the white pixels and then coloring those nearby pixels white as well. Finally, we're just about done. We can now look at this rightmost image and just look at the connected components, or look at the contiguous white regions and draw bounding boxes around them. And in particular, if we look at all the white regions, like this one, this one, this one, and so on, and if we use simple heuristic to rule out rectangles whose aspect ratios look funny, because we know that boxes around text should be much wider than they are tall. And so if we ignore the thin, tall blobs like this one and this one, and if we discard these ones because they're too tall and thin, and we then draw bounding rectangles around the ones whose aspect ratio, that is, whose height to width ratio looks right for text regions, then we can draw rectangles, the bounding boxes, around this text region, and that text region, corresponding to the Lulubee's Antique Mall logo, this Lulubee's, and this little open sign over there. This example, by the way, actually misses one piece of text. This is very hard to read, but there's actually one piece of text there that says Lulubee's again, corresponding to this, but the aspect ratio looked wrong, so we discarded that one. So, looks okay on this image, but in this particular example, the classifier actually missed one piece of text. It's very hard to read because there's a piece of text written against a transparent window. So that's text detection using sliding windows. And having found these rectangles with the text in it, we can now just cut out these image regions and then use later stages of the pipeline to try to read the text. Now, you recall that the second stage of the pipeline was character segmentation. So given an image like that shown on top, how do we segment out the individual characters in this image? So what we can do is, again, use a supervised learning algorithm with some set of positive and some set of negative examples. What we're going to do is look at an image patch and try to decide, is there a split between two characters right in the middle of that image patch? So for each of the positive examples, if you look at this first positive example, this image patch looks like the middle of it is indeed, the middle has splits between two characters. In the second example, again, this looks like a positive example because if I split two characters by putting a line right down the middle, it looks like a good thing to do. So these are positive examples where the middle of the image represents a gap or a split between two distinct characters. Whereas the negative examples, well, you don't want to split two characters right in the middle, you don't want to split two characters like that, and so these are negative examples because they don't represent the midpoint between two characters. So what we do is we would train a classifier, maybe using a neural network, maybe using a different learning algorithm, to try to classify between the positive and negative examples. Having trained such a classifier, we can then run this on this sort of text that our text detection system has pulled out. So we start by looking at that rectangle and we ask, gee, does it look like the middle of that green rectangle, does it look like the midpoint between two characters? And hopefully the classifier will say no. Then we slide the window over, and this is a one-dimensional sliding windows classifier because we're going to slide the window only in one straight line from left to right. There's no different rows here, there's only one row here. But now with the classifier in this position, we ask, well, should we split those two characters, or should we put a split right down the middle of this rectangle? And hopefully the classifier will output y equals 1, in which case we will decide to draw a line down there to try to split two characters. Then we slide the window over again, Hopefully class says don't put a split there, slide over again, hopefully it says yes, do split a split there, and so on, and we slowly slide the classifier over to the right, and hopefully you'll classify this as another positive example, and so on. And we would slide this window over to the right, running the classifier on every step, and hopefully it'll tell us, what are the right locations to split these characters up into, to split this image up into individual characters. And so that's 1D sliding windows for character segmentation. So here's the overall photo OCR pipeline again. In this video, we've talked about the text detection step, where we use sliding windows to detect the text, and we also use a one-dimensional sliding windows to do character segmentation, to segment out this text image into individual characters. And then the final step of the pipeline is the character classification step, and that step you might already be much more familiar with the earlier videos on supervised learning, where you can apply a standard supervised learning, again, maybe a neural network, maybe something else, in order to take as input an image like that and classify, which alphabet, or which of 26 characters A to Z, or maybe which of 36 characters if you have the numerical digits as well. But it'd be a multi-class classification problem where you take as input an image containing a character and decide what is the character that appears in that image. So that was the photo OCR pipeline, and how you can use ideas like sliding windows classifiers in order to put together these different components to develop a photo OCR system. In the next few videos, we'll keep on using the problem of photo OCR to explore some more interesting issues surrounding building an application like this. We've seen over and over that one of the most reliable ways to get a high-performance machine learning system is to take a low-bias learning algorithm and to train it on a massive training set. But where do you get so much training data from? Turns out that in machine learning, there's a fascinating idea called artificial data synthesis. This doesn't apply to every single problem, and to apply to a specific problem often takes some thought and innovation and insight. But if this idea applies to your machine learning problem, it can sometimes be an easy way to get a huge training set to give to your learning algorithm. The idea of artificial data synthesis comprises of two main variations. The first is if we're essentially creating data from whole corpus, creating new data from scratch. And the second is if we already have a small labeled training set and we somehow amplify that training set, or use a small training set to turn that into a larger training set. And in this video, we'll go over both of those ideas. To talk about the artificial data synthesis idea, let's use the character recognition portion of the photo OCR pipeline, where we want to take as input an image and recognize what character it is. If we go out and collect a large labeled dataset, here's what the dataset would look like. For this particular example, I've chosen a square aspect ratio, so we're taking square image patches, and the goal is to take an image patch and recognize the character in the middle of that image patch. And for the sake of simplicity, I'm going to treat these images as grayscale images rather than color images. It turns out that using color doesn't seem to help that much for this particular problem. So given this image patch, we'd like to recognize that that's a T. Given this image patch, we'd like to recognize that that's an S. Given that image patch, we'd like to recognize that that's an I, and so on. So all of these are examples of raw images. How can we come up with a much larger training set? Modern computers often have a huge font library, and if you use a word processing software, depending on what word processor you use, it might have all of these fonts and many, many more already stored inside. And in fact, if you go to different websites, there are, again, huge free font libraries on the internet where you can download many, many different types of fonts, hundreds or perhaps thousands of different fonts. So if you want more training examples, one thing you can do is just take characters from different fonts and paste these characters against different random backgrounds. So you might take this alphabet C and paste that C against a random background. And if you do that, you now have a training example of an image of the character C. So after some amount of work, it is a little bit of work to synthesize realistic looking data, but after some amount of work, you can get a synthetic training set like that. every image shown on the right was actually a synthesized image where you take a font from maybe a random font downloaded off the web, and you paste an image of one character or a few characters from that font against a sort of random background image, and then apply, maybe little blurring operators, maybe little affine distortions, affine meaning just a shearing and scaling and little rotation operations. And if you do that, you get a synthetic training set like the one shown here. And this is work, right? It takes thought and work in order to make the synthetic data look realistic. And if you do a sloppy job in terms of how you create the synthetic data, then it actually won't work well. But if you look at these, the synthetic data actually looks remarkably similar to the raw data. And so by using synthetic data, you have essentially an unlimited supply of training examples for artificial data synthesis. And so if you use this sort of synthetic data, you have essentially an unlimited supply of label data to train a supervised learning algorithm for the character recognition problem. So this is an example of artificial data synthesis where you're basically creating new data from scratch. You're just generating brand new images from scratch. The other main approach to artificial data synthesis is where you take examples that you currently have. So where you take a raw example, maybe from raw image, and you create additional data so as to amplify your training set. So here's an image of a character A from a raw image, not a synthesized image. And I've overlaid this with the grid lines, just for the purpose of illustration. It shouldn't actually have these grid lines, of course. But what you can do is then take this alphabet A, or take this image, and introduce artificial warpings or artificial distortions into the image, so that you can take the image A and turn that into 16 new examples. So in this way, you can take maybe a small label training set and amplify your training set to sort of suddenly get a lot more examples out of it. Again, in order to do this for a particular application, it does take thought and it does take insight to figure out what are reasonable sets of distortions or what are reasonable ways to amplify, to multiply your training set. And for the specific example of character recognition, introducing these warpings seems like a natural choice, but for a different machine learning application, there may be different distortions that might make more sense. Let me just show one example from a totally different domain of speech recognition. So in speech recognition, let's say you have audio clips and you want to learn from the audio clip to recognize what were the words spoken in that clip. So let's say you have one labeled training example. So let's say you have one labeled training example of someone saying a few specific words. So let's play that audio clip here.
0, 1, 2, 3, 4, 5.
All right, so there's some counting from 0 to 5, and so you want to try to apply a learning algorithm to try to recognize the words said in that. So how can we amplify the data set? Well, one thing we can do is introduce additional audio distortions into the data set. So here I'm going to add background sounds to simulate a bad cell phone connection. When you hear beeping sounds, that's actually part of the audio track. There's nothing wrong with your speakers, but let me play this now.
0, 1, 2, 3, 4, 5.
Right, so you can listen to that sort of audio clip and recognize the sounds. That seems like another useful training example to have. Here's another example, noisy background.
0, 1, 2, 3, 4, 5.
Cars driving past, people walking in the background. Here's another one. And so taking the original clean audio clip, so taking the clean audio of someone saying 0, 1, 2, 3, 4, 5, we can then automatically synthesize these additional training examples and thus amplify one training example into maybe 4 different training examples. So let me just play this final example as well.
0, 1, 2, 3, 4, 5.
Right, so by taking just one labeled example, we had to go to the effort to collect just one labeled example of the 0, 1, 2, 3, 4, 5. And by synthesizing additional distortions, by introducing different background sounds, we've now multiplied this one example into many more examples without much work, by just automatically adding these different background sounds to the clean audio clip. Just one word of warning about synthesizing data by introducing distortions. If you're trying to do this yourself, the distortions you introduce should be representative of the sorts of noises or distortion that you might see in the test set. So for the character recognition example, the warpings we introduce are actually kind of reasonable, because an image A that looks like that's could be an image that we could actually see in the test set. Let's look at factor A. And if that image on the upper right, that could be an image that we could imagine seeing. And for audio, well, we do want to recognize speech even against a bad cell phone connection and against different types of background noise. And so for the audio, we're again synthesizing examples that are actually representative of the sorts of examples that we want to classify or want to recognize correctly. In contrast, usually it does not help to add purely random or meaningless noise to your data. Not sure you can see this, but what we've done here is taken the image, and for each pixel in each of these 4 images, just added some random Gaussian noise to each pixel. So each pixel is the pixel brightness, and if you just add some, maybe Gaussian random noise to each pixel, just sort of totally meaningless noise, right? And so unless you're expecting to see these sorts of pixel-wise noise in your test set, this sort of purely random meaningless noise is less likely to be useful. But the process of artificial data synthesis, it is, a little bit of an art as well, and sometimes you just have to try it and see if it works. But if you're trying to decide what sorts of distortions to add, do think about what are the meaningful distortions you might add that will cause you to generate additional training examples that are at least somewhat representative of the sorts of images you expect to see in your test set. Finally, to wrap up this video, just want to say a couple words more about this idea of getting lots of data via artificial data synthesis. As always, before expending a lot of effort, figuring out how to create artificial training examples, it's often good practice to make sure that you really have a low bias classifier and that having a lot more training data will really help. And the standard way to do this is to plot the learning curves to make sure that you have a low bias or high variance classifier. Or if you don't have a low bias classifier, one other thing that's worth trying is to keep increasing the number of features that you classify as, so increasing the number of hidden units in your neural network, say, until you actually have a low bias classifier. And only then should you put the effort into creating a large artificial training set. So what you really want to avoid is to spend a whole week or spend a few months figuring out how to get a great artificially synthesized data set, only to realize afterward that your learning algorithms and performance doesn't improve that much, even when you give it a huge training set. So that's sort of our usual advice of testing that you really can make use of a large training set before spending a lot of effort going out to get that large training set. Second is, when I'm working on the machine learning problems, one question I often ask the team I'm working with, that I often ask my students, which is, how much work would it be to get 10 times as much data as we currently have? When I face a new machine learning application, very often I'll actually sit down with the team and I'll ask exactly this question. I've asked this question over and over and over. And I've been very surprised how often this answer has been that, it's really not that hard. It's maybe a few days of work at most to get 10 times as much data as we currently have for a machine learning application. And very often, if you can get 10 times as much data, there will be a way to make your algorithm do much better. So, if you ever join a product team working on some machine learning application product, this is a very good question to ask yourself and ask the team. And don't be too surprised if after a few minutes of brainstorming, if your team comes up with a way to get literally 10 times as much data, in which case I think you would be a hero to that product team, because with 10 times as much data, I think you might really get much better performance just from learning from so much data. So there are several ways to try to get a lot more data, and in this video we focus mainly on the idea of artificial data synthesis, and that comprised both the ideas of generating data from scratch using the random fonts and so on, as well as the second idea of taking an existing example and introducing distortions to amplify, to enlarge the training set. A couple other examples of ways to get a lot more data are to collect the data or to label it yourself. So one useful calculation that I often do is ask, how many minutes, how many hours does it take to get a certain number of examples? So I should sit down and figure out, suppose it takes me 10 seconds to label one example. Then, and suppose that for our application, currently we have 1,000 labeled examples. So 10x as much of that would be if m would equal to 10,000. Right, so a second way to get a lot of data is to just collect the data and label it yourself. So what I mean by this is I will often sit down and do a calculation to figure out how much time, like just how many hours would it take, how many hours or how many days would it take for me or for someone else to just sit down and collect 10 times as much data as we have currently by collecting the data ourselves and labeling ourselves. So for example, let's say that for a machine learning application, currently we have 1,000 examples, so m equals 1,000. Then what we'll do is sit down and ask, well, how long does it take me really to collect and label one example? And sometimes maybe it'll take you, 10 seconds to label one new example. And so if I want 10x as many examples, I do a calculation. If it takes me 10 seconds to get one training example, if I want to get 10 times as much data, then I need 10,000 examples. So I do the calculation. How long is it going to take me to manually label 10,000 examples if it takes me 10 seconds to label one example? So when you do this calculation, often I've seen many teams be surprised at how little work, sometimes a few days of work, sometimes a small number of weeks of work, but I've seen many teams be very surprised at sometimes how little work it could be to just get a lot more data and let that be a way to give you learning outcome, a huge boost in performance. And as I said earlier, sometimes if you've just managed to do this, you will be a hero in whatever product development or whatever team you're working on, because this can be a great way to get much better performance. Third and finally, one sometimes good way to get a lot of data is to use what's now called crowdsourcing. So today there are a few websites or a few services that allow you to hire people on the web to fairly inexpensively label large training sets for you. So this idea of crowdsourcing or of crowdsourced data labeling is something that has its own sort of entirely academic literature, has some of its own complications and so on pertaining to labeler reliability. If you have hundreds or thousands of labelers around the world working fairly inexpensively to help label data for you, and the lecturer mentioned this as one alternative as well. And probably Amazon Mechanical Turk system is probably the most popular crowdsourcing option right now. But this is often quite a bit of work to get to work if you want to get very high quality labels, but it's sometimes an option worth considering as well. If you want to try to hire many people to fairly inexpensively on the web label large amounts of data for you. So in this video, we talked about the idea of artificial data synthesis, of either creating new data from scratch, like using the random fonts in an example, or by amplifying an existing training set by taking existing labeled examples and introducing distortions to it to sort of create extra labeled examples. And finally, one thing that I hope you remember from this video is this idea of, if you're facing a machine learning problem, it's often worth doing two things. One, just sanity check with learning curves that having more data would help. And second, assuming that that's the case, I would often sit down and ask yourself seriously, what would it take to get 10 times as much training data as you currently have? And not always, but sometimes you may be surprised by how easy that turns out to be. Maybe a few days or a few weeks of work, and that can be a great way to give your learning algorithm a huge boost in performance. In earlier videos, I've said over and over that when you're developing a machine learning system, one of the most valuable resources is your time as the developer in terms of picking what to work on next. Or if you have a team of developers or a team of engineers working together on a machine learning system, again, one of the most valuable resources is the time of the engineers or the developers working on the system. And what you really want to avoid is if you or your colleagues or your friends spend a lot of time working on some component only to realize after weeks or months of time spent that all that work just doesn't make a huge difference on the performance of the final system. In this video, what I'd like to do is talk about something called ceiling analysis. When you have a team working on a pipeline machine learning system, this can sometimes give you a very strong signal, a very strong guidance on what parts of the pipeline might be the best use of your time to work on. To talk about ceiling analysis, I'm going to keep on using the example of the photo OCR pipeline. And as said earlier, each of these boxes, text detection, character segmentation, character recognition, each of these boxes can have even a small engineering team working on it, or maybe the entire system is just built by you, either way. But the question is, where should you allocate resources? And of which of these boxes is most worth your effort trying to improve the performance of? In order to explain the idea of ceiling analysis, I'm going to keep using the example of our photo OCR pipeline. As I mentioned earlier, each of these boxes here, each of these machine learning components, could be the work of even a small team of engineers. Or maybe it could be the whole system could be built by just one person. But the question is, where should you allocate scarce resources? That is, which of these components, or which one or two, or maybe all three of these components is most worth your time to try to improve the performance of? So here's the idea of ceiling analysis. As in the development process for other machine learning systems as well, in order to make decisions on what to do for developing the system is going to be very helpful to have a single row number evaluation metric for this learning system. So let's say we pick character level accuracy. So given a test set image, what is the fraction of alphabets of characters in the test set image that we recognize correctly? Or you can pick some other single row number evaluation metric if you want, but let's say that for whatever evaluation metric we pick, we get that we find that the overall system currently has 72% accuracy. So in other words, we have some set of test set images, and for each test set images, we run it through text detection, then character segmentation, then character recognition, and we find that on our test set, the overall accuracy of the entire system was 72% on whatever metric you chose. Now, here's the idea behind ceiling analysis, which is that we're going to go to, let's say, the first module of our machine learning pipeline, say text detection. And what we're going to do is we're going to monkey around with the test set. We're going to go to the test set, and for every test example, we're just going to provide it the correct text detection outputs. Right? So in other words, we're going to go to the test set and just manually tell the algorithm where the text is in each of the test examples. So in other words, we're going to simulate what happens if we have a text detection system with 100% accuracy for the purpose of detecting text in an image. And really, the way you do that is pretty simple, right? Instead of letting your learning algorithm detect the text in the images, you would instead go to the images and just manually label what is the location of the text in my test set image, and you would then let these correct or let these ground truth labels of where is the text be part of your test set, and just use these ground truth labels as what you feed in to the next stage of the pipeline, to the character segmentation pipeline. Okay, so just to say it again, by putting a check mark over here, what I mean is I'm going to go to my test set and just give it the correct answers, give it the correct labels for the text detection part of the pipeline. So that is as if I have a perfect text detection system on my test set. What we're going to do then is run this data through the rest of the pipeline, through character segmentation and character recognition, and then use the same evaluation metric as before to measure what is the overall accuracy of the entire system. And with perfect text detection, hopefully the performance will go up, and in this example, let's say it goes up 89%. And then we're going to keep going. Next, let's go to the next stage of the pipeline, to character segmentation. So again, I'm going to go to my test set, and now I'm going to give it the correct text detection output and give it the correct character segmentation output. So let's go to the test set and manually label the correct segmentations of the text into individual characters, and see how much that helps. And let's say it goes up to 90% accuracy for the overall system. Right? So as always, the accuracy is the accuracy of the overall system. So whatever the final output of the character recognition system is, whatever the final output of the overall pipeline is, going to measure the accuracy of that. And then finally, I'm going to go to the character recognition system and give that the correct labels as well. And if I do that too, then no surprise, I should get 100% accuracy. Now, the nice thing about having done this analysis is we can now understand what is the potential upside, the upside potential for improving each of these components. So we see that if we get perfect text detection, our performance went up from 72 to 89%. So that's a 17% performance gain. So this means that if we take a current system and we spend a lot of time improving text detection, that means that we could potentially improve our system's performance by 17%. It seems like it's well worth our while. Whereas in contrast, when going from text detection, when we gave it perfect character segmentation, performance went up only by 1%. So that's a more sobering message. It means that no matter how much time you spend on character segmentation, maybe the upside potential is going to be pretty small, and maybe you do not want to have a large team of engineers working on character segmentation if this sort of analysis shows that, even when you give it the perfect character segmentations, your performance goes up by only 1%. So this really estimates what is the ceiling or what's an upper bound on how much you can improve the performance of your system by working on one of these components. And then finally, going from characters, when we get better character recognition, the performance went up by 10%. So, again, you have to decide, is a 10% improvement, how much is that worth your while? But this tells you that maybe with more effort spent on the last stage of the pipeline, you can improve the system. You can improve the performance of the systems as well. Another way of thinking about this is that by going through this sort of analysis, you're trying to figure out, what is the upside potential of improving each of these components, or how much could you possibly gain if one of these components became absolutely perfect, and this really places an upper bound on the performance of that system. So the idea of ceiling analysis is pretty important. Let me just illustrate this idea again, but with a different example of a more complex one. Let's say that you want to do face recognition from images. So let's say you want to look at the picture and recognize, whether or not the person in this picture is a particular friend of yours, or whether try to recognize the person shown in this image. This is a slightly artificial example. This isn't actually how face recognition is done in practice, but I want to step through an example of what a pipeline might look like to give you another example of how a ceiling analysis process might look. So we have a camera image, and let's say that we design a pipeline as follows. Let's say the first thing you want to do is do pre-processing of the image. So let's take this image like I have shown on the upper right, and let's say we want to remove the background. So do pre-processing, the background disappears. Next, we want to, say, detect the face of the person. That's usually done with a learning algorithm. So we'll run a sliding windows classifier to draw a box around the person's face. Having detected the face, it turns out that if you want to recognize people, it turns out that the eyes is a highly useful cue. We actually, in terms of recognizing your friends, the appearance of their eyes is actually one of the most important cues that you use. So let's run another classifier to detect the eyes of the person. So segment out the eyes, and then since this will give us useful features to recognize the person, and then other parts of the face, the particular interest, maybe segment out the nose, segment out the mouth, and then having found the eyes, the nose, and the mouth, all of these give us useful features to maybe feed in to a logistic regression classifier, and it's the job of the classifier to then give us the overall label, the final label for who we think is the identity of this person. So this is a kind of complicated pipeline. It's actually probably more complicated than you should be using if you actually want to recognize people. But there's an illustrative example that's useful to think about for ceiling analysis. So how do we go through ceiling analysis for this pipeline? Well, we'll step through these pieces one at a time. Let's say your overall system has 85% accuracy. The first thing I do is go to my test set and manually give it the ground truth foreground background segmentation. So manually go to the test set and use Photoshop or something to just tell it where's the background, and just manually remove the background, so this is the ground truth background, and see how much the accuracy changes. In this example, the accuracy goes up by 0.1%. So this is a strong sign that even if you had perfect background segmentation, your performance, even if perfect background removal, the performance of your system isn't going to go up that much. So it's maybe not worth a huge effort to work on pre-processing, on background removal. Then we can go to the test set, give it the correct face detection images, then again step through the eyes, nose, mouth segmentation in some order. Just pick one order. Let's give the correct location of the eyes, correct location of the noses, correct location of the mouth, and then finally, if I just give it the correct overall label, I get 100% accuracy. And so, as I go through the system and just give more and more components the correct labels in the test set, the performance of the overall system goes up, and you can look at how much the performance went up on different steps. So, from giving it the perfect face detection, it looks like the overall performance of the system went up by 5.9%. So that's a pretty big jump. It means that maybe it's worth quite a bit of effort on better face detection. Went up 4% there, it went up 1% there, 1% there, and 3% there. So it looks like the components that are most worth our while are when I gave it perfect face segmentation, face detection, system went up by 5.9 performance. When I gave it perfect eye segmentation, it went up by 4%, and then my final logistic classifier well, there's another 3% gap there maybe. And so this tells us maybe what are the components that are most worth our while working on. And by the way, I want to tell you a sort of true cautionary story. The reason I put in this pre-processing background removal is because I actually know of a true story where there was a research team that actually literally had two people spend about a year and a half, spend 18 months working on better background removal. They're actually, I'm obscuring the details for obvious reasons, but there was a computer vision application where there was actually a team of 2 engineers that literally spent, I think, about a year and a half working on better background removal. Actually worked out really complicated algorithms, so ended up, I think, publishing one research paper. But after all that work, they found that it just did not make a huge difference to the overall performance of the actual application they were working on. And if only someone were to do a ceiling analysis beforehand, maybe could have realized this. And one of them said to me afterward, if only they'd done a sort of analysis like this, maybe they could have realized before that 18 months of work that they should have spent their effort focusing on some different component than literally spending 18 months working on background removal. So to summarize, pipelines are pretty pervasive in complex machine learning applications. And when you're working on a big machine learning application, I think your time as a developer is so valuable. So just don't waste your time working on something that ultimately isn't going to matter. And in this video, we talked about this idea of ceiling analysis, which I've often found to be a very good tool for identifying the component that if you actually put a focus effort on that component and make a big difference, it will actually have a huge effect on the overall performance of your final system. So over the years, working in machine learning, I've actually learned to not trust my own gut feeling about what component to work on. So very often, I've worked on machine learning for a long time, but often I'll look at a machine learning problem and I may have some gut feeling about, oh, let's jump on that component and just spend a lot of time on that. But over the years, I've come to even trust my own gut feelings or learn not to trust gut feelings that much. And instead, if you have a sort of machine learning problem where it's possible to structure things, to do a ceiling analysis, often that's a much better and much more reliable way for deciding where to put a focus effort to really improve the performance of some component and be kind of reassured that when you do that, it will actually have a huge effect on the final performance of your overall system.